pleasure to introduce our next speaker, Professor Suganidis from Chicago, and he will speak on scalar conservation laws with rough stochastic dependence.
Thank you very much. Thank you for the invitation. I like this thing. I was here in the previous program. I gave a talk, and this gives you some kind of feeling of power when you have this spear here that allows you to do things. So if anybody doesn't behave, excuse me? That's the point. I mean, I cannot be as good as you are on that, Peter. Anyway, so what I want to talk is some recent work with Benoit Pertam and Pierre-Louis Lyons about scalar conservation laws with stochastic flux and some stochastic averaging lemmas. I don't think there is only one word that I will use later in my talk that connects me with this workshop, so there are not going to be any models or whatever. It's more like a theory in need of applications more than the other way around. Although I can name applications. Okay, so now let's figure out how to do that. All right, so the kind of equations I have in mind is let's say scalar conservation law, where I don't want anybody to get too much into the stochastic thing here. Just think of that as W as a rough path, as something that a priori doesn't have derivatives. And we'll see how we go along with that. So I'm writing it as a differential, but don't be obsessed with that. Think of W being something smooth. This will be then a real derivative. And the whole point is to have a theory that does not rely on the regularity of W. The usual assumptions on A, so C2, whatever, we can take them W, all of them to be the same or to be a vector. Brownian motion is a special case, and just for those of you who are familiar with a little bit stochastic calculus, if W happened to be a Brownian motion, this circle here is used to denote what is known as a Stratonovich differential. And I will explain in a minute what that is. So don't worry about that. And if it is not Brownian, forget it. And as I said, these are the kinds of applications I have in mind. Equations like that come up naturally when you study hydrodynamic limits of particle systems and you are outside the regime where the law of large number applies. Then you are left with something stochastic in the end, which unfortunately is space-time white noise, not just time white noise, and nothing I'm going to say applies to space-time white noise. But nevertheless, that's one way to get it. It has also appeared as a model in one of the things that Lyons has worked recently on mean field games. So it's one equation that comes up naturally as a mean field equation. The other one is just mathematical curiosity, and you will see from the talk how this thing comes up. And the last one is whether you have regularizing effects due to averaging, which is something that has already appeared in another work by Flandoli, where when you look at the linear transport equation of the Ambrosio-Lyons-Di-Perna theory, if you add a stochastic term, then it turns out you can remove a lot of the assumptions on the vector field just because you have some randomness in the problem. So randomness tends to shake things around, so when you average, you get better regularity than you had before. And I will try to show that later at the end of the talk. Okay, so let's see whether... All right, now let me take care of this Stratonovich versus Ito, because you may be familiar with the usual stochastic differential equation, or stochastic D, where there is no circle. And then basically, at least at the formal level, when you write an equation like that, you mean this. Now, I'm not claiming that this is a shorthand notation, so the theory is more than just saving yourself from the trouble to write all that stuff, but at least at the formal level, this circle means that. Where now dW without a circle is the usual Ito's formula. And so that's at the formal level. So in our equations, there is a hidden second order term like that, which plays no role, of course. And now let me explain why. So that's the relationship. Now let me explain why one should look at why is it natural to look for Stratonovich versus Ito. So the first is that if you want to have a theory that is dense under smooth approximations, you have to use Stratonovich. Meaning if you want to have a theory that says that if the W's are smooth, but somehow converge locally uniformly to a Brownian motion, then what you're going to get in the end is Stratonovich. So Stratonovich is the calculus for which you have chain rule improbability, and is the calculus for which you can do the simplest problem. Okay. So let me explain that. Suppose we do a d, stochastic d, dx, the simplest thing in one d. So let's take first an ODE like that. So in 1D, then of course you can think of the solution as being a function of that, where the capital X solves this equation, which is an autonomous equation. This is a trivial case, right? I'm in 1D. I'm just trying to motivate something. So given that, if I put here now an epsilon, then I will have throughout an epsilon. And if I tell you that W epsilon goes to W, let's say locally uniformly, then of course at the limit you are going to get this. And our stochastic calculus tells you that this capital X solves right. So it is a natural notion of it's the natural thing to do if you want to have density under smooth approximations. And that's a kind of result we are going to have, that we are going to approximate the W by smooth things, and then we're going to pass to the limit. And the second is, if you want to have well-posedness, you are forced to use Stratonovich versus Ito. You can guess that because there is this hidden second-order term, but the easiest way to understand that is to think of this very trivial equation. And here, purposely, I haven't put a circle or a dot or anything. So I put ux dw. Again, anything I say, if you're confused with the dw, think of w being smooth and then dw is a real derivative. So let's take this to be a real derivative. Then, of course, you make this change. This is a parenthesis missing here. So you make that change. And then clearly you see, if you use the usual stochastic calculus, that v should solve this equation. So you started with a problem that everybody who sees it will say, sure, it has to be well posed. After all, we are conditioned to know that if we put uxx with a small parameter in front, no matter how small, the problem is regular. But you see that if I don't put a circle there, I come down to an equation which is not well posed if lambda is less than a half. Because that's exactly the half it's missing. Half ux is missing up there. While if this is now Stratonovich, so if I had a circle here, then this function will solve exactly that problem and will be smooth. So if you expect to have something that is well posed, you better think of it in the sense of Stratonovich. Now, I repeat, I will use very little of stochastic calculus. So I'm just trying to make a point why it's necessary to look at Stratonovich and not Ito. Okay, now possible extensions of what I'm going to describe. I haven't even given you a result, but let's go at the level of extensions. One is, you notice I didn't have an x dependence before in the flux. Now, if I put an x dependence on the flux, the problem becomes technically more complicated. And here, the stochastic properties will play a role. And the only reason we don't have that yet is level of its technicality. The other is semilinear rough dependence. So now I have what I had before, the stochastic flux, but now I'm adding a semilinear term. I'm assuming the f is very nice. So this is not an issue of blow up or whatever, global ellipsis, whatever you like it to be. W tilde is another rough path or Brownian motion or whatever, and that's the notation I'm using. And the reason I would like to consider this problem is because the method I'm going to show you has a natural interpretation when you are dealing with this problem. And we don't know yet how to conclude. And this is very interesting from the point of view of the kinetic theory. Finally, one could extend that to quasi-linear. I mean, you can start putting noise. You can do quasi-linear conservation laws of that form. And again, that's something one could try to do. And the last thing is you may want to think of systems where now you put a stochastic perturbation. So these are the possible extensions at different degree of difficulty. All right, now let me describe some other works, relative works, and one of which I'm related to it, and now that was the real, when I said mathematical curiosity, that was the real reason we got into this problem. So one important work that I should mention is the work by Debus and Vauvel, and independently by Feng and Nullard, and also by Chen, Ding, and Carlson. Debus, Vauvel, and Feng Nullard are considering space-time white noise, and they are doing the ethos formulation for the problem, and they are able to prove for W being W tilde being there is no stochastic flux. The flux is really deterministic, so they are just putting a semi-linear perturbation to the conservation law in the ethos sense, and they are able to develop a kinetic formulation and a well-posed theory for the problem. And the second related work, which was the motivation we had to do, that gave us the motivation to study this problem, is the theory of stochastic viscosity solutions that I've been developing with Lyons, and which applies to equations of that form up there at the Hamilton-Jacobi level. And keep in mind that, of course, in dimension 1, there is this equivalence between Hamilton-Jacobi and conservation law. So it's reasonable to expect that some of the general principles behind that theory may be used to study the stochastic conservation law. Okay. Now let me take you through the difficulties one has to study such a theory, to have such a theory. So everybody knows there are no global smooth solutions in general, which takes away the fact that you cannot interpret the equation. Remember, how do you interpret a stochastic DE? It never makes sense when you write it down, so you always interpret it by integrating. So to make real good sense of the problem here, you're going to have to integrate in time, but to do that you need to have global regularity, because you're going to have to integrate the derivatives, and if you don't have global regularity, you cannot do it. The second difficulty is that any kind of weak notion of solution you can think, either for the Hamilton-Jacobi equation or for the conservation law, requires that at some places you can evaluate the equation. At some points, maybe not many, but at some places you have to be able to evaluate the equation. And this is out of the question here, because the W is plus minus infinity almost surely, so there is no way. After all, I said we are dealing with W's that are not differentiable. Okay. The next thing is you cannot use inequalities, because again the W can be plus infinity, minus infinity, so any notion of entropy solution or viscosity solution, whatever, goes out the window, because you cannot write less equals 0. You are not allowed to do that. The next one is that you have the issue of shocks, and that's an important issue here, because think of a W that goes up and down. All right, so you go forward in time, let's say you go past the shock, but W oscillates, so in principle you could come back, and you may have to go over the shock again, and these problems don't let you do that. In particular, a naive way to study, let's say, this problem in 1D with one Brownian motion is to do what I did here for the stochastic D, namely think of the solution as being a change. After all, it's a multiplicative noise, and you can think of the solution as being the just change of time for some universal equation, exactly as I did here for the ODE. But now you see here the difficulty I'm describing. Solutions of this problem will have shocks, and there is no way you're going to go back and forth through the shock. So whatever theory you do, you have to deal with the fact that on the one hand, there are some cancellations that are happening because you go up and down, but this it cannot be a complete cancellation. The other thing is that there is no general probabilistic theory that one can use here. And when you do the linear elliptic equations, for example, there is this wonderful theory which goes under the name of martingale theory, developed by a number of people, Vardan and Struck in particular, which allows you to define some kind of distributional solution, but this cannot be done here for two reasons. Once, the problem is nonlinear, so you cannot really integrate by parts completely, and the second is you lack the compactness. So let me explain to you a little bit at the context of the heat equation what does the martingale theory do? So the martingale theory is based on the following idea. Solving this stochastic differential equation is basically equivalent to solving this PD. If I know how to solve this PD for any initial data, that's equivalent to having a solution in law of that stochastic OD, stochastic D. So in analogy, if you want to solve, let's say, this stochastic PD, you should be able to find the equation that carries all the information, the same way the heat equation carries all the information for the stochastic D. And the equation for the stochastic PD, the relative equation, is this equation. I forgot, okay, which is now an infinite dimensional equation. And this is a second derivative in infinite dimensions. And this operator is unbounded in whatever norm you're going to do. You lack estimates. And the issue here, of course, is the fact that it's nonlinear inside. The difficulty here is the nonlinearity you have. If the problem is linear, that's what the martingale theory does. So there is no theory for that. Okay. So these are the basic difficulties one faces. So you either give up or you try to do something else. And to motivate what we are doing, because once you see it, you're going to say this looks too ad hoc, is I have to explain to you a little bit the key idea behind the notion of the stochastic viscosity solution. And so bear with me. This is now, I'm outside the scope of the conference. So I'm going to deal with this stochastic Hamilton-Jacobi equation. I don't care about a lot of generalities, putting sums there, many things. And let's also take H to be smooth so I can write down derivatives. Now, again, quickly remind you what is the definition of viscosity solution. I'm writing it in a way that, as I said before, doesn't make any sense because the W, I mean, I cannot write inequalities, but again, think of W being smooth right now. So function V is a subsolution. Anytime you have a local maximum, when you take a smooth function phi, you look at the local maximum of V minus phi, and at that point, you can evaluate the equation with an inequality. And that's exactly the problem I said. If W is rough, namely has no derivatives, then there is an issue to do that. But nevertheless, that's the definition of the solution. Okay, now, is there something, however, okay, so I mentioned all the difficulties that one has to study this equation, but in particular the lack of regularity, but are there any regular solutions to the problem? And the answer is yes. And all of us learn quickly in PD that for these kinds of equations, if you use characteristics, you have at least a short time regular solutions. So there are characteristics for the deterministic Hamilton-Jacobi equation, and there are characteristics for the stochastic Hamilton-Jacobi equation, and the characteristics are there. So I wrote them down. For you, these are the characteristics. So instead of being ODs, they are stochastic Ds, or if we take W to smooth, these are ODs. Okay. So there's a theorem that if you do it in the stochastic case, you need to worry a little bit about measurability issues that says that you are always having, for any smooth data, you are always having a short time smooth solution. And if the problem is random, there will be the interval of existence will be random, and of course will depend on the second derivative of the H and the second derivative of the initial data, and that's why it's local. So we always have a short time solution to the problem if we start with smooth data. Okay, so keeping that in mind, this is how we define the stochastic viscosity solution. Instead of looking for a maximum of V minus an arbitrary test function, we take a smooth phi, we solve locally the Hamilton-Jacobi equation, and we use now this function, which is the short time solution of the Hamilton-Jacobi equation, as a test function. The result of that is that formally gets rid of the H, and you are left with this inequality. Let me explain a little bit in a heuristic way what we do there. So abstractly, it's like wanting to solve a problem like that. And what we are doing, we're saying, okay, suppose I bring this on this side. And suppose I can find a function V such that V dot is U dot minus BU. As I said, this is generalized nonsense what I'm writing there. Then, of course, V dot will be some A tilde of phi. And that's what we are doing there. So At the level where everything is smooth, we are able to absorb the stochastic term, and we are left with something that, if there were, for example, second-order derivatives there, will be random, but random in the sense that the equation is random, but doesn't have white noise anymore. So that's the idea behind it. We already saw me doing that at the level of this equation, because what I said there was if uxt is u of x minus wt, or the other way around, v, then I wrote down that vt solve that. Of course, the problem here is linear, so everything works out perfectly. If the problem here was nonlinear, I will have an f that is going to be a more complicated thing. But so the idea of the stochastic viscosity solution is adjust your test functions to get rid of the stochastic part, and then you are left with something which is now a deterministic equation in the sense there is no Brownian motion anymore with random coefficients. Why does this thing, and it turns out this silly trick works, and one can have a global theory for stochastic viscosity solutions for the fully nonlinear problem and so on. So in some sense, this is consistent with the spirit of viscosity solutions, which is you can know, as long as you can find test functions to do the job, you should have a theory. However, it's a little bit difficult because the theory of viscosity solutions, and so I'm not going to say anything more about viscosity solutions, but let's conclude here. The theory of viscosity solutions also relies very much on the fact that you can use any test function you like. And in this case, I cannot use any test function I like. My test functions here are very robust, are short-time solutions of an equation, which means you have not much flexibility. You have to work very hard to do anything with these equations. And now let me explain the idea of RAF. So there is actually there's a probabilist in Oxford, a colleague of Alexis Terry Lyons, who has put forward an algebraic type of theory about how to solve equations with stochastic differential equations with RAF paths. And more or less the idea is that you are interested, they designed this room very well, but okay, I can go there. So I'll use sigma again. And so the idea of Terry Lyons is think of x as a function of w. All right? And so he has developed an algebraic theory that says, an algebraic type theory that says you can solve, no matter what w is, you can have a solution to that problem, having the solution as a function of w in some complicated way. And as long as if you go back to what I said here, as long as I can solve this system of characteristics up there, I can always have a theory. All right, so I can do any other path than RAF path. Okay, so I'm just saying that because I want to all right, now let's go to the stochastic conservation laws. And let's recall a little bit what we know about conservation laws, not in this audience. Of course, I would like to define an entropy solution, and I will run exactly at the problems I described earlier with inequalities, because entropy solutions should do that. And if the W is a Brownian motion, or I always passing to the limit, I will have a problem with inequality. So I cannot do that. I cannot apply that definition the same way I could not apply the definition of viscosity solutions. Now, at that level, you say, okay, do the trick, do the same thing you did before, and it should work. It's not clear how to do it, because the characteristics don't come into this game at all. They play, I mean, it's a global, somehow, constraint. However, you can do it at the kinetic formulation level. And now I'm justifying why I'm giving this talk here. I use the word kinetic, so I'm at least one part of the title and one part of the title of the conference. I have to say something to say about that. Okay. So what I'm going to do is I want to use the kinetic formulation to carry out the program I described earlier through the characteristics and see whether we can get something out of it. All right. So again, at this audience, I don't have to remind. I just put it there. That's the formulation I want to write, and I'm writing it down freely again because W can be smooth. Or if you like, this equation as a stochastic D now is a very nice equation because it's basically A is not depending on xi, so we can do whatever we want with that. All right, so let me continue now with some preliminaries, how to define the notion of the stochastic entropy solution. So I rewrote here the equation, and I'm doing the same thing I did before. I'm solving locally the equation, or global if you like here, because it's linear, for some smooth initial data. So I take some nice rho 0, and if I write down the function that I have up there, the rho of y, x, whatever, if I write down this function, this is nothing else but the solution to that equation. Problem is linear, so these are the characteristics, and this is a solution to that. And I don't have to worry here about invertibility because there is no x dependence. That's why I said that the x dependent problem is more complicated. If there is an x there, then I will have to worry about local time invertibility of the characteristics. And then I'm arguing formally, if rho is a solution of that problem and chi is a solution of that problem, then the product clearly solves that equation. And once you have that equation, here, you can integrate it, and a miracle over Rn, the derivative here kills the stochastic term, and you are left with this identity, which of course you have to interpret in the sense of distributions in xi. So you have this this identity here, that when you integrate the solution of the kinetic formulation against a kernel which you build like that, which is a short time solution of your of the problem, W disappears and you are left with that. And W really disappears because look what happens here. The only thing that comes into rho is not anymore W dot. I shouldn't say W disappears. The derivative of W disappears. The only thing that comes into rho is W. So this is something that is random but doesn't have the difficulties of the having to take derivative on the white noise. And on the right hand side you have this quantity. And what I'm saying here, again, it can be justified at the level of W being smooth. And okay, so the regularity of W is not important. Once I come down to this equation, if I come in and tell you, okay, I have this equality here in the sense of distributions and T and xi, and rho is defined like that, W just have to be a continuous function. So there is no reason anymore to worry about whether W is differentiable or not. Integration, okay. Now it turns out that using this formula you can obtain the usual estimates. All the estimates that one has for the kinetic theory that in the original work of Eitan with Benoit and Pierre-Louis, you can carry them in this case because W is smooth, so all of them. And all the estimates are independent of the regularity of W because I have integrated out W dot. And okay, that's for technical reasons. One of these identities that's necessary. So this identity, which is also correct, some identity like that, which holds in the case of where you didn't have the W term, will hold here too. So I mean, this is just something that is in the background. So let's not worry about that. The important thing is, but by using this formulation here, I have eliminated the lack of regularity of W, and W now is just a continuous function. Note, by the way, that if I were to write this thing in the sense of distribution, so I integrate against test functions, and if I had W epsilon going to W, rho epsilon will go to rho. So I have this thing I was alluding before, that I have density passing to the limit independently of the regularity of W just by pathwise convergence. Okay, so this is the definition of the stochastic entropy solution we're going to give. We're going to say that we have a stochastic entropy solution when this identity holds in the sense of distributions for rho's that have this form. If I had an x dependence once more in the flux, I will have to write this thing only for short time because I cannot invert the characteristics globally if there is an x dependence. Okay, so that's the definition. So the definition is the formula we got, assuming that W is smooth, And we got a formula, once again, that does not depend on the regularity of W, and this is what I'm going to claim now as being a solution. All right, so I always tell when I teach a class in PDE that you can define chairs to be solutions. The question is, what can you do with them? And so it turns out that one can prove that there exists a unique solution in that sense for W rough, for W just a continuous path. You can prove a contraction principle. You have a contraction for two solutions, and you can even obtain a very precise estimate for the error you make when you have solutions corresponding to two different paths. And I want to walk you through this estimate because, okay, this is under the assumption that the initial data is BV. So you see now that the problem is a little bit non-trivial. If it was the case that I could write a solution, I mean, given everything I said so far, you would think that the difference of two solutions will depend at time t, will depend on W1 minus W2 at time t. And that would have been the case if, let's say, u of xt was u of x. You would expect something like that to be true, that the solution to depend only on W at t, to depend on W2 minus W1 at t. But you see the solution depends in a much more complicated way. It depends on the full path of the W you have here. So at any time t, the solution depends on the soup of the difference up to time t. And that is what makes the solution, the problem more complicated. It's not anymore a t by t dependence. It has to see the whole path. And okay, so how does one prove something like that? Once you have the definition, it's just a matter of hard work to prove, let's say, the estimate. And basically what you do is you follow along the lines of what Benoit had done to prove uniqueness of solutions to scalar conservation laws using the kinetic formulation. So I will walk you through some series of identities which will become more and more complicated. So you start with a formulation for both solutions. You subtract them, you get this inequality here. Let's see where I can make this work. No. Now I caused the problem. How do I fix this? Does anybody know? Control L. Control L. So clearly this didn't work. Okay, so now I produce, again, I'm sure most of you have seen this kind of proof. Now I write down this quantity, and then you start writing identities. Everything you do here works because you don't have to differentiate any more W. So everything is nice. You integrate by parts. You use the fact, as in the proof of Benoit, that the cross terms between the measure and the Dirac masses have signs, whatever you have. And then you come up to a complicated and long identity that tells you that this derivative, which was up there, is controlled by the right terms. So at that point, what you do to conclude is you choose a whole family of test functions, which are basically like that. You use the BV bounds, you use the probabilities of chi, you let eta go to 0, and you pass the limit. Once more, I want to stress, to emphasize here, if there is anything here, is the definition and the fact that it works, rather than these technical things which are long and tedious, and you have to carry them out. But you have already encoded all the information on the definition. Okay. All these arguments are going to be more complicated if you allow for x dependence in the flux, in which case what you're going to have to do is, since you can only invert the characteristics locally, you're going to have to define the notion of the solution in a local way, and you're going to have to iterate in time to carry a whole interval. And there, the difficulty you're going to have is that the interval of existence of these smooth solutions now will depend on the second derivative of rho 0. And therefore, you are going to have to carry that information with you, and that will involve introduce some assumptions on the x dependence on the flux, as it does for the Hamilton-Jacobi case. Okay, now that we went to this issue of stochastic averaging lemma, and I start with the most trivial case of that equation. Of course, everything I'm going to say can be generalized if here you had a nonlinear term A of psi under the appropriate non-degeneracy conditions on A. Okay, so that's the problem we want to see. And we want to see that when you integrate the solution against we integrate over psi, whether we can get some regularization for rho, and to compare the possible results we get here to what is known for the case where there is no dW. That's just identity, which is the classical averaging lemma. So I take W to be a Brownian motion, and I'm going to write down a series of estimates, and I will compare them with the deterministic case. So if there is no right-hand side, and for any positive lambda, you get this estimate. And if you see, as I'm going to write immediately afterwards, in the deterministic case, you don't have this lambda square root there. And that's consistent with the scaling of the Brownian motion. Here I'm dealing with real Brownian motion. I'm taking expectation, so I will have to use the properties of the Brownian motion. Okay? Now if I start with 0 initial data and allow a g, then I get an estimate like that, L2 h a half, which is again what you know from the classical theory. You don't see any improvement there, but the improvement comes at this point, where if you assume that the right-hand side is really divergence, here you can go up to a third, while the classical result that did not have Brownian motion was just the W. You see these are similar, but the presence of this extra lambda minus a half is the thing that allows you to gain here derivative from a quarter to a third. So there is an improvement in the regularization you have due to the fact that once you take expectations, the things are more regular than they were before. And I mentioned that. Let me now remark this thing about suppose you have a vector, a function b, and its ellipse is continuous, and you write this difference. Then, of course, omega by omega, or point-wise, you are not going to get anything more than the regularity of the Brownian motion, which is pretty pitiful in this case. However, if you decide to take a square here, and then you take some expectation, you can compute here something. And when you compute here, you find that this is some function of, let me put t minus s to some power. And then there is an elementary theorem from probability that says if you have something like that, then almost surely this is like and that's the kind of regularization I'm talking about. That if you just use a W as an arbitrary Hölder continuous path, and B ellipses, you cannot get anything more than what is the assumption on W. But if it happens to be a Brownian motion, just because you can integrate and you get some explicit rate here, there is a basic result in probability that tells you that actually, almost surely, you were more regular than you would have gotten before. So there is some regularization there. The way I'm writing it is not correct, but let's not worry about that. Okay, so the points I'm making here is number one, we have an improvement for a quarter to third. And okay, that I mentioned that we can generalize. Now, what I want to do here is I like to show you a little bit of proof. And the reason is, I mean, we came up with this proof first looking at a very nice paper by De Villet and Busseau about another way of proving averaging lemmas for the time-dependent problem. But we are not following their proof. Actually, we are presenting a proof that is, we believe, simpler than what they are doing and more transparent. Okay. So I don't remember exactly what the Villette, and we showed it in their paper, but they're using, I think, a Laplace transform as something for the ODE. What we're doing is we're just taking Fourier transform of f in x. So I'm writing this problem down here, and as usual in that game, we added this lambda f hat on both sides. Now we are in a trivial situation. We can write down explicitly the solution. It's nothing more than that. It's variation of constants formula. And if you integrate against psi, this is exactly the formula. So now we have a closed formula for the thing we want to estimate. We want to estimate the L2 norm of this thing, so we take a square. All up to here is trivial Cauchy-Schwarz, and now what we're going to do is we're going to hit it with expectation. So we have an expectation of that term, and we have an expectation of that term. And the hope now is that because we are averaging, something better is going to come out of that. And I'm going to show you only the calculation with the lambda minus a half. It's not, I think, so late in the day worth seeing more than that. So we estimate each term separately, and this is the calculation. And this is it. I mean, this is as explicit as you can make it, except the last step, except this inequality. So up to here is just equality. I take the case where g is 0 now. So I only have to worry about the first term. So I take g0, so I only have to worry, let's say, about that term and the term with the lambda, but let's forget about that. So I'm just going to estimate this term. And I think the beauty of the method is that you can do the thing explicitly. There's no complicated calculations here or anything. So you compute this expectation, you do what you have to do, you put things together, and at that point, I'm using now the fact I have a Brownian motion, so I can compute this expectation explicitly and get a term like that. So the message here is that I'm using that, I'm averaging against the Brownian motion, and I come down with a fairly explicit integral, which I can compute one extra step by using this calculation. And that quantity I want to estimate is exactly this. It's exact. Now, the obvious thing to do there is to try to do Cauchy-Schwarz, and then it fails. So if you look at this thing in a more a little bit, not more sophisticated, but in a little bit different way, you see that actually you can get a term like that, which is what was the square root of lambda I was mentioning, and the 1 over k is the thing that gives you the regularization at that level. Okay, so how do you do that? And I'm going to conclude, I guess, with this. So we don't do Cauchy-Schwarz here. You choose a base on the xi space, which the first vector is in the direction of k. In the orthogonal direction, you just do Cauchy-Schwarz. And in the direction of that, you just do Young's inequality. So this is just in the direction of vector k. You do Young's inequality, and all this computation reduces to this explicit integral there. So now, if you do the g term, the thing is more complicated, but because of the fact you already have the 1 over square root of lambda here, you're going to be able to gain the regularity when you put the g, which is diverges. Okay, I think I gave you enough time to eat lunch. I can stop here. Thank you very much.
Thank you very much for the nice talk. There's already the first question.
First of all, since it's on the board here, where do you use the f has to be non-degenerate? Otherwise,
no. Not f. It doesn't have to be non-degenerate. I said if I put a of psi instead of psi, then a has to be non-degenerate.
Yeah, but where do you use it? Do you use it?
Because at that level here, I will have an a of psi1 minus a of psi2. So when instead of having psi1 minus psi2 here, I will have a psi1 minus a psi2. And I will have to worry about how to estimate that in terms of psi1.
So you just hide it, okay.
So it's a very explicit computation. And I think it makes also the paper of, we said, the Villette much simpler to read, because this is it. If it is deterministic, you don't have to do a lot of these steps.
And the second thing, so coming back to the basic idea. So the basic idea is that if you go from the conservation law to the kinetic formulation, it enables you to take this multi-valued solution and then you have all this stochastic averaging. It can do whatever it wants there. There are no shocks, basically. And then by averaging, you just select the right things.
If you want to see the averaging lemma. If you want to have a weak theory, there is no averaging there or anything. You have to do it more explicitly there. The only idea, the main idea is that you absorb the randomness. Okay, so to explain that better, I have to let me write one more thing. After all, I have some time. You don't have to stay. So the easiest way to think about it is to think of that problem. Okay, so now I have a combination of a regular flux and a stochastic flux. So what I do here with this formulation is I do exactly what I described. I do it at the kinetic formulation level. I do exactly what I said there at the form what I said formally. So somehow I'm inverting this nonlinear problem. So I'm saying this thing is some Vt for some function of V, and that then U is some function, I don't know how to write it, for V. So that problem changes. And that's what we are doing. That's the concept. That's the concept of solution we are using. The only point is we are doing at the level of the kinetic formulation because this thing doesn't make any sense there. So along these lines, I wanted to mention this. Where did I do this thing? Okay. Now, why am I interested in the semi-linear problem here? And that's a question for the experts here. So again, 1D to make life simple. And let me put also a dt there, just to make, and let me even put that away. And f is very nice. So this is not a question of blow-up. I would like to repeat the same thing here, namely say, all right, I write that. Now what I do is I solve this equation here with initial data at u. I write u as phi of t v. I plug it in, and I do exactly the calculation I was talking before, because now this is a global thing, I can do it. And then v will solve an equation which will be that. Yeah, if everything is smooth, what I did is exact, and there is no questions about that. And so now I'm asking the question, is an entropy solution of the first problem, if I have u to be an entropy solution of the first problem, and I can define an entropy solution here, there is nothing to worry about that, is v an entropy solution to this problem? And if you write down the viscosity approximation, you see you pick an extra term. Which means that if you were to write down the kinetic formulation at the right-hand side, you are not going to have only the derivative of a measure, but you are going to have an extra term, which will be the weak limit of the extra term you get when you do the viscosity approximation. Nevertheless, this should be correct in some sense, that with a kinetic formulation with an extra term on the right-hand side, instead of just the derivative of a portion of no negative measure, this should be okay, because I'm not doing much here. This is a global transformation that should work, because this is a global smooth transformation. The fact it depends on time is the thing that makes the thing work, otherwise it will be trivially false. Right? If you look at ut plus ux equals 0, and you take a function of u, that is not going to be an entropy solution, but there is the time that adjusts everything. And so right now we have some minor difficulty even at that level, let alone putting the w there, to come up exactly with what is the entropy solution to that problem coming from this transformation. Because put here a lambda uxx and carry the transformation, you're going to see you're going to pick an extra term. which doesn't go to 0 at the limit. So it should give you something. And this should be possible to do it because this is a natural way to study this problem. And why is natural? Because it has worked at least for at least 2 classes of equations I know rather nonlinear. And I doubt that it fails here, right? With the appropriate modifications. Okay.
Any other questions?
Just a comment. It seems that you had to struggle more for this than in the Hamilton-Jacobi case.
No.
Although, no?
As a matter of fact, no.
I think
This is, compared to Hamilton-Jacobi case, is trivial. The main reason is
because you have
the main reason is that the kinetic formulation, the characteristics are invertible globally, and I don't have to worry about anything. If I put an x dependence, then I will have to struggle. However, let me just say, to my surprise, this step, which is trivial at the Hamilton-Jacobi level, is not trivial here. At the Hamilton-Jacobi level, going from ux here to that problem is trivial. Of course, I have to change the a. But at the level of the conservation law, so that's a place where it's non-trivial, although at the Hamilton-Jacobi is trivial.
second comment. You shortly refer to the rough paths theory. I mean, is it? Can they do something like that using their?
Okay, so there is there are 2 paths, and okay, now we're getting into this chauvinistic type of thing with Peter. The reason I present it like that is the following. Rough paths are at the level of the D, a differential equation, not at the level of the PD. So if you use rough paths and you are able to solve the system of characteristics, then you plug it into this thing and it works. All right?
If you get the same notion of solutions.
Yeah, I mean, everything works because that's why I'm separating it to the system of the characteristics and the PD. All right? Now, rough paths are a little bit, okay, let me say one thing about that because I keep saying it. All right. Let me do again 1D, this stochastic D. All right? Then I said the solution, this is 1D. The solution is some global equation like that, where solve this. So what Terry Lyon's trying to do with rough paths is to generalize this notion. So here you can say that the solution of that equation is a function of the path. So you give me a path, that's the solution. But of course, I'm in 1D, everything is trivial. Now let's go multi-D. So now this is n is bigger than 1. Now I cannot do this anymore. The natural thing to say is that, okay, this is now, let's say n equals 2. The natural thing to say is, okay, this depends on the whole path, on W1 and W2. But of course, it's nonsense, because then you lose that structure. So what rough path says is, the rough path theory say that the solution of that problem is indeed some function. Now it's not as a simple function. Okay, this x is not that, which is the path, as I had here, and it sees also these integrals. Okay, so it sees these Levy integrals. So the solution is a function not only of the path, but also these double integrals. Okay? And that's what rough path says. So then you develop a theory at that level where now your space is paths plus these integrals, and the complication is that if you want to have a dense, if you want to have a theory that is closed under approximations, it's not enough to put a W epsilon here and say W epsilon goes to W. W epsilon has to go to W, and these double integrals have to go to the corresponding things, which of course then forces you to have certain restrictions on the regularity you have, and there is a recent work of Lyon's about that, about what is the optimal regularity you can have to do that. Okay, so that's rough path. So as long as you have that, then you can do the characteristics, you can do that.
Any last question?
Okay, so
So thank you very much again.